something is escaping. Not the way light escapes from an ordinary star streaming outward in all directions, weakening with distance, carrying energy and information across the cosmos in the gentlest possible way. Something is escaping from the most extreme environments in the observable universe, from the immediate vicinity of supermassive black holes, from regions where the gravitational field is so intense that the escape velocity approaches the speed of light, from conditions so violent and so dense that the physics predicts the energy should be trapped, absorbed, destroyed before it can reach us. And yet, it arrives. High-energy gamma rays, photons carrying millions to billions of times the energy of visible light, produced in processes so extreme that they can only occur in the vicinity of the most massive and most energetic objects in the universe, are reaching the Fermi Gamma-ray Space Telescope from directions that correspond to the hearts of active galactic nuclei, from regions within light days of supermassive black holes, from environments that the physics says should be opaque to exactly this kind of radiation. They shouldn't get out. The physics is clear about this. In the dense radiation fields surrounding an actively accreting supermassive black hole, high-energy gamma rays should collide with lower energy photons and produce electron-positron pairs, annihilating themselves before they can escape. The region near the black hole is a trap, not just for matter, but for the highest energy light. The opacity should be overwhelming, and yet the gamma rays are here, not faint, marginal detections at the edge of the instrument's sensitivity. Bright, energetic, sustained emission from blazars, from active galactic nuclei, from regions so compact that the variability timescales tell us the emission must be originating within a volume smaller than our solar system, in the immediate vicinity of a black hole containing billions of solar masses. Something is escaping that the physics says can't escape. And the Fermi telescope, arguably the most important high-energy astrophysics observatory ever built, has been documenting this impossibility in extraordinary detail for over 15 years. But that's not the only thing Fermi found, because in 2010, when astronomers carefully subtracted the known sources of gamma-ray emission from Fermi's map of the sky, removing the contribution from cosmic rays, from pulsars, from supernovae, from all the known astrophysical gamma-ray sources, they found something that nobody had predicted, something that had been hiding in the data, invisible against the bright gamma-ray glow of the Milky Way, until the analysis was careful enough to see it. Two enormous structures, symmetric, one above and one below the plane of the Milky Way, extending 25,000 light years in each direction from the galactic center, containing the energy equivalent of 100,000 supernovae, shaped like bubbles, or like the exhaust plumes of an unimaginably powerful engine, pointing directly toward the supermassive black hole at the center of our galaxy. Something escaped from Sagittarius A. Not recently, the structures are millions of years old. But at some point in the past, our galaxy's central black hole, which today appears quiescent, barely consuming any material, barely producing any radiation, did something so energetic that its exhaust is still visible today, 25,000 light years away, glowing in gamma rays that the Fermi telescope can detect from Earth, the Fermi bubbles, two of the most extraordinary structures in the Milky Way. And nobody knew they were there before Fermi looked. Something escaped. Something is still escaping. And understanding what and how is one of the most important problems in high-energy astrophysics. Let me start with the instrument itself, because understanding what Fermi can do, what makes it uniquely capable of seeing what it sees, is essential for appreciating what its discoveries mean. The Fermi Gamma-ray Space Telescope was launched in June 2008 and placed in a low Earth orbit at an altitude of 565 kilometers. It carries two instruments, The primary instrument, the Large Area Telescope, or LAT, is a pair conversion telescope. It detects gamma rays by allowing them to enter a tracker filled with tungsten foil layers, converting each gamma ray into an electron-positron pair, and then tracking those particles through a calorimeter that measures their energy. The resulting measurement gives both the direction and the energy of each incoming gamma ray with extraordinary precision. The LAT covers the energy range from about 20 MeV megaelectron volts to more than 300 GeV gigaelectron volts. To put this in perspective, visible light photons have energies of roughly 2 to 3 electron volts. The photons that Fermi's LAT detects carry energies 1 billion times higher. These are the most energetic photons that occur in nature, produced only in the most extreme astrophysical environments. The second instrument, the Gamma Ray Burst Monitor, or GBM, covers a lower energy range from 8 keV to 40 MeV and monitors the entire unocculted sky for the brief, intense flashes of gamma radiation called gamma ray bursts. The GBM has detected thousands of gamma ray bursts since launch, including the extraordinary GRB 221009A, the brightest gamma ray burst ever recorded, which we discussed in an earlier conversation. Together, these two instruments have given us the most comprehensive map of the gamma ray sky ever assembled. Not a snapshot, a continuous 15-year monitoring program that has watched thousands of sources vary in brightness, detected transient events from milliseconds to years in duration, and mapped the diffuse gamma ray emission from our galaxy and beyond with a resolution and sensitivity that was previously unimaginable. What Fermi sees is the extreme universe, the universe of the highest energies, the most violent processes, the most extreme physical conditions, black holes accreting at near maximum rates, pulsars spinning hundreds of times per second, supernova remnants accelerating particles to near light speed, the mysterious dark matter annihilation that might be producing gamma rays from the galactic center. And through all of this extreme emission from all of these extraordinary sources, something is escaping that the physics says shouldn't be able to. Let me take you first to the blazars, because the blazar story is the one where the impossibility is most precisely quantified, where the physics gives you a specific prediction about what should and shouldn't escape, and the Fermi data contradicts that prediction in a way that requires a fundamental revision of how we think about the most energetic processes near black holes. A blazar is a specific type of active galactic nucleus, a galaxy, with a supermassive black hole at its center that is actively accreting material and producing a relativistic jet, not a typical active galactic nucleus, a specific subset in which the jet is pointed almost directly toward Earth. The alignment means we're looking straight down the barrel of the jet, seeing the emission Doppler boosted by the relativistic motion of the jet material. The result is the most luminous, persistent objects in the observable universe. Blazars can outshine their entire host galaxy with its hundreds of billions of stars by factors of thousands. Their emission spans the entire electromagnetic spectrum, from radio waves to the highest energy gamma rays. And they vary on time scales from years down to minutes, sometimes seconds, in ways that tell us about the specific physical conditions in the jet. The gamma ray emission from blazars is where the physics becomes most interesting and most problematic. The Fermi-LAT detects gamma rays from hundreds of blazars. Some of these gamma rays have energies above 100 GeV. Some have energies in the TeV range detectable by ground-based Cherenkov telescopes that operate above 100 GeV, instruments that catch the brief flashes of blue light produced when the gamma rays interact with Earth's upper atmosphere. And here's the problem. The region around an actively accreting supermassive black hole is not empty. It's filled with photons, soft X-rays from the hot accretion disk, ultraviolet radiation from the corona, infrared photons from the dusty torus surrounding the black hole. This photon field is dense, extraordinarily dense by astrophysical standards, and it presents a specific physical obstacle to high-energy gamma rays. When a high-energy gamma ray encounters a low-energy photon, the two can interact to produce an electron-positron pair, a process called gamma-gamma pair production. The threshold energy for this process depends on the energy of the target photon. A 100 GeV gamma ray can pair produce on ultraviolet photons. A 10 GeV gamma ray requires X-ray photons, and so on. The cross-section for this process, the probability per unit path length of the pair production interaction occurring, depends on the density of the target photon field. In the immediate environment of an actively accreting supermassive black hole, the photon field is dense enough that the pair production opacity, the attenuation suffered by high-energy gamma rays traveling through this field, should be enormous. The mean free path for a 100 GeV gamma ray in the radiation field near a blazar should be far shorter than the distance from the gamma ray production site to the edge of the broad line region. The gamma rays should be absorbed before they can escape. The calculation is straightforward. Given the measured luminosity of the blazar, which tells you the photon density in the radiation field and the known cross-section for pair production, which quantum electrodynamics predicts with extraordinary precision, you can calculate what fraction of the gamma rays should survive to escape the nuclear region. For many blazars, the calculation gives a survival fraction that is essentially zero. The environment should be completely opaque to the observed gamma rays. And yet Fermi and the ground-based Cherenkov telescopes detect them bright, variable, clearly originating from within the nuclear region based on the variability timescales. Something is escaping that cannot escape. The resolution to this paradox has been one of the most productive controversies in high-energy astrophysics over the past 15 years. And the solution, or rather the set of solutions, has revealed something fundamental about how the jets of active galactic nuclei work. The key insight is the variability. Not just that blazars are variable, that was known before Fermi, but the specific timescales of the variability, how fast the gamma ray brightness changes, and what those timescales imply about the size and location of the emission region. In special relativity, no signal can travel faster than the speed of light. If a source of emission varies on a timescale of 1 day brightening and fading within 24 hours, then the emission region cannot be larger than 1 light day across. Otherwise, the light travel time from different parts of the region would smear out the variability. Fermi has detected blazars varying on timescales of minutes, not days, minutes. The famous blazar PKS 2155 to 304 showed variability with a doubling time of 2 minutes during an exceptional flare in 2006 detected by the Hess Cherenkov telescope array. The Fermi-LAT has since detected similarly rapid variability in multiple blazars. 2 minutes. The emission region must be smaller than 2 light minutes across smaller than the distance from Earth to the Sunday. Now compare this with the size of the supermassive black hole. The Schwarzschild radius, the event horizon radius of a black hole with a mass of 1 billion solar masses is roughly 3 billion kilometers, about 2.8 light hours. The emission region implied by the 2-minute variability, a few light minutes across, is a fraction of the Schwarzschild radius. The gamma rays are being produced within a small fraction of the event horizon radius. In this region, this tiny volume, a fraction of the event horizon from the black hole, the photon density is highest. The pair production opacity is most extreme. the gamma rays are least able to escape. And yet they're varying on 2-minute timescales, implying that whatever produces them is operating at this precise, impossibly opaque location. The resolution lies in the relativistic jet itself. The jet is not stationary. It's moving at near light speed with Lorentz factors of 10 to 50 or more. This relativistic motion transforms the physics in a specific and important way. In the rest frame of the jet material, the frame moving with the plasma, the photon density of the surrounding radiation field is reduced by the relativistic transformation. Photons that appear energetic and dense in the lab frame appear less energetic and more diluted in the jet frame. The pair production opacity calculated in the jet rest frame is dramatically lower than a naive lab frame calculation would suggest. The escape is powered by relativistic motion. The jet is moving fast enough that the ambient photon field appears, from the jet's perspective, too diluted and too low energy to efficiently absorb the gamma rays before they escape. The relativistic beaming that makes blazars so luminous, amplifying the emission by factors of thousands because the jet is pointed at us simultaneously, reduces the opacity seen by the gamma rays in the jet frame. This resolution is elegant. It works quantitatively for many blazars, but it doesn't work for all of them. There are specific cases where the inferred Lorentz factor required to make the opacity low enough exceeds anything that current jet formation models can produce, and the implied emission sizes based on variability are sometimes so small that even extreme relativistic beaming can't fully resolve the opacity problem. Something is still escaping that even the relativistic jet explanation can't fully account for. Let me now take you to the specific recent Fermi finding that I think is most physically profound, the one that goes beyond the blazar opacity problem and reveals something unexpected about the structure of the magnetic fields near black hole event horizons. In 2021 and 2022, a team analyzing years of Fermi lat data from the blazar TXS 0506 plus 056, the same blazar associated with the first multi-messenger detection of a high-energy neutrino from an astrophysical source, identified a specific pattern in the gamma-ray variability, not just rapid variability indicating a compact emission region, quasi-periodic oscillations, a rhythmic brightening and fading, with a period of roughly 34 days, repeating over multiple cycles, embedded in the more chaotic overall variability, quasi-periodic oscillations in X-ray binaries. Stellar mass black holes accreting material in binary star systems are well known, well understood. They arise from specific resonances in the accretion disk, from orbital frequencies near the innermost stable circular orbit, from precession effects in the curved space-time near the black hole. Their periods in X-ray binaries are seconds to minutes, consistent with the orbital timescales near a stellar mass black hole. For a supermassive black hole, the same physical processes produce oscillations with periods scaled by the mass, millions to billions of times longer. A 3-4 day quasi-periodic oscillation in a blazar containing a black hole of perhaps 1 billion solar masses corresponds to a physical process occurring at roughly the same number of Schwarzschild radii as the comparable process in an X-ray binary. The physics is the same, the scale is different. The specific physical interpretation of the 3-4 day oscillation in TXS 0506 plus 056 involves the lens-Thirring effect, the precession of orbits around a rotating black hole, induced by the frame dragging of space-time. The spinning black hole drags space-time around with it like a spinning ball of dough, twisting the air around it, causing the plane of accretion disk orbits to precess. This precession can modulate the jet direction periodically changing the angle of the jet relative to our line of sight, which changes the Doppler boosting factor, which changes the observed gamma ray brightness. If this interpretation is correct and it's consistent with multiple other lines of evidence, then the Fermi data is directly probing the rotational dynamics of a supermassive black hole. The 3-4 day oscillation is space-time itself precessing around a spinning black hole. It's the Lense-Thirring effect, the frame dragging of curved space-time encoded in gamma-ray photons that traveled billions of light years to reach us. Something is escaping, not just gamma rays. Information about the geometry of space-time in the immediate vicinity of a rotating black hole. Now let me take you to the Fermi bubbles, because this is where the escaping from a black hole story becomes most personal, where the black hole in question is not billions of light years away, but at the center of our own galaxy, 26,000 light years from Earth. When the Fermi-Lat science team first published the map of the gamma-ray sky in 2010, after 2 years of survey observations, one of the analysis tasks was to subtract the known contributions to the diffuse gamma-ray emission. Cosmic rays interacting with the interstellar gas produce a diffuse glow through the plane of the Milky Way, the brightest feature in the gamma-ray sky, overwhelming everything else in the galactic plane. Known point sources, blazars, pulsars, supernova remnants are subtracted individually. What remains after all the known contributions are removed is the residual emission, the gamma rays, that the models don't account for. In 2010, Mungsu, Tracy Sladier, and Douglas Finkbeiner, analyzing the first-year Fermi-Lat data, identified the residual emission above and below the galactic plane with a clarity that previous studies had missed. 2 enormous lobes of excess gamma-ray emission, symmetric about the galactic plane, centered on the galactic center. They call them the Fermi bubbles. The dimensions are staggering. Each bubble extends roughly 25,000 light years from the galactic plane, half the distance from Earth to the galactic center, in a direction perpendicular to the galactic disk. The 2 bubbles together span 50,000 light years from tip to tip. In comparison, the entire disk of the Milky Way is about 100,000 light years in diameter. The Fermi bubbles occupy an enormous fraction of the volume of the Milky Way's halo. Their edges are sharp, not diffuse, not gradually fading into the background, but precisely defined boundaries where the gamma-ray emission drops sharply. Sharp edges mean a specific physical process created the boundary, not gradual diffusion of relativistic electrons through the halo, but a specific expanding front, like the blast wave of an explosion or the boundary of a jet-inflated cocoon. Their spectrum is hard flatter than the spectrum of cosmic ray-induced emission from the galactic disk. The gamma-ray photons in the bubbles have energies extending to tens of GeV with a spectral shape that is more consistent with inverse Compton scattering relativistic electrons boosting CMB photons to gamma-ray energies than with pion decay from cosmic ray interactions with gas. And they're centered with extraordinary precision on Sagittarius A times a supermassive black hole at the center of the Milky Way. Something escaped from Scree A. Something so energetic that its exhaust filled a volume of space 50,000 light years across and is still glowing in gamma rays millions of years later. What was it? This is the question the Fermi bubbles have been posing since their discovery. And 15 years of multi-wavelength follow-up observations in X-rays with Chandra and XMM Newton, in radio with the Meerkat Array, in ultraviolet with the Hubble Space Telescope, have assembled a picture of what happened. Not a complete picture, not a resolved picture, but a picture with specific constraints that rule out some hypotheses and support others. The 2 leading hypotheses are a past AGN outburst, a period when Scree A times was actively accreting material at a much higher rate than today, and producing powerful jets and a nuclear starburst, a period of intense star formation near the galactic center, with the cumulative energy from thousands of supernovae and stellar winds driving a galactic wind that inflated the bubbles. Both hypotheses have observational support and observational challenges. The AGN outburst hypothesis is motivated by the morphology. The sharp edges of the Fermi bubbles are more consistent with jet-inflated lobes than with the more diffuse structure expected from a starburst-driven wind. The symmetry, the near-perfect reflection symmetry about the galactic plane, is more naturally explained by two oppositely directed jets from the central black hole than by the more distributed energy input from a starburst. Specific support for the AGN hypothesis came from Hubble Space Telescope observations in 2020, published by Gupta and collaborators, that detected specific absorption features in the ultraviolet spectra of background quasars, whose light passes through the Fermi bubbles. The absorption features correspond to specific silicon and carbon ions moving at specific velocities outflowing from the galactic center at roughly 900 to 1,100 kilometers per second. The velocity structure is more consistent with a jet-driven outflow than a starburst-driven wind. Additional support came from eROSITA, the X-ray telescope aboard the Russian-German Spectre RG satellite, which published in 2020 the detection of two enormous X-ray structures that largely coincide with the Fermi bubbles, but extend even further, reaching 45,000 light-years from the galactic plane, compared to the Fermi bubbles' 25,000. The eROSITA bubbles are hotter and less sharply defined than the Fermi bubbles, suggesting they represent the shock-heated gas surrounding the relativistic plasma that produces the gamma-ray emission. The timing of the event, when did scirate times undergo the outburst that created the bubbles, is constrained by the dynamics of the structures. The bubbles have been expanding into the halo for some period of time. The longer they've been expanding, the further they extend. Given the observed extent and the inferred expansion velocity, the outburst that created them occurred roughly 2 to 4 million years ago. 2 to 4 million years ago, when our Australopithecus ancestors were walking the African savanna before Homo sapiens existed, before our genus existed. The central black hole of the Milky Way erupted, producing jets of relativistic plasma that inflated the structures we now call the Fermi bubbles, and then fell silent again. Today, scirate times is quiescent. It's accreting material at a tiny fraction of its past rate. The jets are gone. But the exhaust is still there, still glowing in gamma rays, still expanding slowly into the halo, still visible to the Fermi telescope. Something escaped from our galaxy's central black hole. A colossal amount of energy, 100,000 supernova equivalents, was released in jets that punched through the galactic disk and inflated enormous structures that now dominate the gamma ray sky above and below the galactic plane. And we're only now discovering this with a telescope that was launched in 2008 and that has been patiently, systematically mapping the gamma ray sky for 15 years. Let me close this first part with something that I think captures the full significance of what Fermi has been doing and what the escaping from black hole story ultimately means for our understanding of the universe. Black holes are defined in the most basic sense, the sense that most people know by the fact that nothing escapes from them. The escape velocity inside the event horizon exceeds the speed of light. Light itself cannot escape. Information cannot escape. Matter cannot escape. But the universe around black holes is not defined by nothing escaping. It's defined by the most energetic escaping phenomena in the cosmos. The most luminous persistent objects in the universe, quasars, blazars, are powered by black holes and are defined by the energy that escapes their vicinity. The most energetic explosions in the universe, gamma-ray bursts, are powered by black holes and are defined by the jets and photons that escape. The Fermi bubbles, structures 50,000 light years across, containing the energy of 100,000 supernovae, escaped from our own galaxy's central black hole 2 to 4 million years ago and are still visible today. Black holes are the universe's most powerful engines, not despite the fact that nothing escapes from inside them because of it. The energy extracted comes not from the black hole itself, but from the infalling matter in its vicinity, from the magnetic fields wound up by the spinning black hole's frame dragging, from the shredding and heating and acceleration of material as it spirals inward. The black hole takes matter in. The universe, through the extraordinary physical processes operating in the vicinity of the event horizon, converts a fraction of that matter's rest mass energy into the most energetic radiation and particle beams in observable universe. Something is escaping in gamma rays, in jets, in cosmic rays, in the slowly expanding lobe structures that fill the halos of galaxies. In the frame-dragging oscillations encoded in the quasi-periodic variability of blazars. In the ultraviolet absorption features of gas flowing out of our own galactic center at 1,000 kilometers per second, all of this detected, measured, mapped, characterized by the Fermi Gamma-ray Space Telescope over 15 years of continuous monitoring, is telling us something specific about how the most extreme objects in the universe work, about what happens in the magnetic field geometry around a spinning black hole, about how jets form and escape and propagate, about what happens when a supermassive black hole wakes up and erupts and then falls silent again. The physics of something escaping is the physics of how the universe processes energy at its most extreme. And in part 2, I want to go deeper into the specific physics of how the jets form, into what Fermi has revealed about the magnetic field structure near the event horizon, into the mystery of the gamma-ray variability that implies emission from regions smaller than the solar system around billion solar mass black holes, and into something that I think is the most theoretically profound aspect of the entire story. What the escaping particles tell us about the specific geometry of space-time in the immediate vicinity of a rotating black hole. Something is escaping, and following exactly what it is and how it escapes is one of the most productive and most extraordinary programs in modern astrophysics. So we'd arrived at this place where the Fermi Gamma-ray Space Telescope has been documenting for 15 years a specific and extraordinary phenomenon: high-energy gamma rays escaping from the immediate vicinity of supermassive black holes from regions that the physics says should be opaque to exactly this kind of radiation. Quasi-periodic oscillations encoding the frame dragging of space-time around rotating black holes, and the Fermi bubbles, two enormous structures, 50,000 light years across, centered on our galaxy's central black hole, the exhaust of an eruption that occurred 2 to 4 million years ago and whose energy signature is still lighting up the gamma-ray sky. Now I want to go deeper into the specific physics of how the jets form, how a black hole that swallows everything manages to produce the most energetic outflows in the universe, into what Fermi has revealed about the magnetic field structure near the event horizon that makes this possible, into the mystery of the ultra-rapid variability and what it implies about the emission geometry, and into something that connects the blazar observations to some of the deepest questions in theoretical physics, the specific relationship between the magnetic field topology near a rotating black hole, and the extraction of energy from the black hole's spin itself. Let me start with the jets, because understanding how they form, understanding the specific physical mechanism by which a black hole converts infalling matter into collimated beams of relativistic plasma is the foundation of everything else. The standard picture of a jet-producing active galactic nucleus involves three components: the supermassive black hole at the center, the engine, the accretion disk, the fuel supply, and the magnetic field, the mechanism. The accretion disk is a rotating structure of gas and dust infalling toward the black hole. As material loses angular momentum and spirals inward, it heats up through viscous dissipation, through magnetorotational instabilities, through the compressional heating of gas spiraling deeper into the gravitational well. At the innermost regions of the disk, near the innermost stable circular orbit, where the gravitational curvature of space-time first allows stable circular orbits, the temperature reaches tens of millions of Kelvin. The disk glows in X-rays. It radiates an enormous amount of energy. But the disk alone doesn't produce jets. Something in addition to the thermal radiation from the disk is required. And that something is the magnetic field. The infalling gas carries magnetic field with it. As the gas flows inward and the disk rotates, the magnetic field is wound up, amplified, organized, concentrated in the inner disk region. The specific dynamics involve the magnetorotational instability, a specific instability that operates when a weakly magnetized fluid rotates differentially, with inner regions rotating faster than outer regions. This instability drives turbulence in the disk, which amplifies the magnetic field and drives angular momentum outward, allowing the gas to spiral inward. The resulting magnetic field structure near the black hole is specific and important. The field has both a toroidal component wound around the rotation axis by the spinning disk and a poloidal component threading through the disk in the direction of the spin axis. The poloidal component is the crucial one for jet formation. A strong poloidal magnetic field threading the inner accretion disk provides a specific physical environment in which the Blandford-Znaic mechanism can operate. This mechanism, proposed by Roger Blandford and Roman Znaic in 1977, long before Fermi, in a paper that has become one of the most important in the history of astrophysics, is the primary theoretical framework for understanding how relativistic jets are powered. The Blandford-Znaic mechanism is, at its core, a process of electromagnetic energy extraction from a rotating black hole. Let me explain what that means, because it's one of the most extraordinary things in all of astrophysics, and it connects directly to the question of what's escaping from these systems. A rotating black hole, a Kerr black hole, in the language of general relativity, is not just a mass. It's a mass with angular momentum. The spin of the black hole is a source of energy, rotational kinetic energy, just like the rotational kinetic energy of a spinning top or a flywheel. But in the case of a Kerr black hole, this rotational energy is stored in the geometry of space-time itself. The spinning black hole drags space-time around with it, the Lentz-Thirring effect, or frame dragging, creating a region called the ergosphere where nothing can remain stationary. Everything inside the ergosphere must rotate with the black hole. The ergosphere lies outside the event horizon. It's a region of space-time, not a surface, where the frame dragging is so extreme that the drag exceeds the speed of light for a stationary observer. Inside the ergosphere, you can't hover. You must move in the direction of the black hole's spin. But you can still escape. The ergosphere is outside the event horizon, and light can still reach infinity from there. The Blandford-Znaic mechanism works as follows. A magnetic field is threaded through the ergosphere, anchored partly in the accretion disk and partly in the spinning space-time of the ergosphere. The rotation of space-time in the ergosphere twists this magnetic field, driving electrical currents along the field lines. These currents extract energy and angular momentum from the rotating black hole, specifically from the rotational energy stored in the Kerr geometry, and transport them outward along the magnetic field lines. The result is a pointing flux, an electromagnetic energy flux flowing outward along the field lines that thread the ergosphere and the inner disk. This outflowing electromagnetic energy carries momentum. As it flows along the field lines away from the black hole, it accelerates the plasma that permeates the magnetosphere, the region of magnetic field near the black hole. The accelerated plasma becomes the jet, a collimated beam of electromagnetic energy and relativistic particles, flowing outward at near light speed, powered by the rotational energy of the black hole itself. The rotational energy of a maximally spinning supermassive black hole of 1 billion solar masses is approximately 9 × 10^61 joules. This is an almost incomprehensible energy, roughly 10 billion times the energy released by all the stars in the Milky Way over the entire age of the universe. The Blanford-Znayak mechanism can, in principle, tap a fraction of this energy. The efficiency is not 100%, but for highly spinning black holes, the extracted power can be substantial. Something is escaping. The energy of the black hole's own rotation, stored in the geometry of space-time, is being converted into the most energetic, persistent outflows in the universe. Now let me tell you about what Fermi has specifically revealed about the Blanford-Znayak mechanism, about the specific evidence that this theoretical picture is correct. The key observational test involves the relationship between the jet power and the black hole spin. In the Blanford-Znayak picture, the jet power is proportional to the square of the magnetic flux threading the event horizon times the square of the black hole spin parameter. If you can measure the jet power from the radio and gamma ray luminosity and estimate the magnetic flux from the properties of the accretion flow, you can test whether the predicted relationship holds. Fermi has contributed to this test in a specific and important way. The LAT's precise measurement of the gamma ray luminosity of blazars, combined with the modeling of the spectral energy distribution that constrains the particle content and magnetic field strength in the jet, provides estimates of the total jet kinetic power. These estimates, for large samples of blazars observed over years of Fermi monitoring, show a specific correlation with the black hole mass and accretion rate that is consistent with the Blanford-Znayak prediction. More specifically, the blazars with the most powerful gamma ray jets, the ones that are brightest in Fermi's catalog, the ones that show the most extreme variability, are systematically associated with black holes that other lines of evidence suggest are spinning rapidly. The correlation is not perfect. Blazar modeling involves significant uncertainties, but it's consistent and it points in the right direction. The most powerful jets come from the most rapidly spinning black holes, as the Blanford-Znayak mechanism predicts. The most direct test of this connection came from the Event Horizon Telescope, the global network of radio telescopes that produced the first images of a black hole shadow, which we've discussed in other conversations. The specific morphology of the magnetic field in the immediate vicinity of the M87 times black hole, revealed by the EHT's polarization measurements, showed a configuration consistent with a magnetically arrested disk in which the magnetic flux threading the event horizon is near the maximum value that the accretion flow can sustain. A magnetically arrested disk is the specific configuration in which the Blanford-Znayak mechanism is most efficient. The magnetic flux is high. The extraction of rotational energy is maximized. The jet power is at its peak for a given black hole spin and accretion rate. The EHT polarization image of M87 times was showing us the engine of the jet, the specific magnetic field configuration at the boundary between the accreting plasma and the black hole's event horizon that drives the relativistic outflow that Fermi detects as gamma-ray emission from the blazar 1,000 light-years downstream. Now let me tell you about something that Fermi has revealed that goes beyond the individual blazar observations, a discovery that has transformed our understanding of the relationship between black hole activity and galaxy evolution on the largest scales. We've established that the Fermi bubbles in the Milky Way represent the exhaust of a past AGN outburst. But the Milky Way is not unique. Every large galaxy has a central supermassive black hole, and many of them show evidence of past or present activity. The question is, how does this black hole activity affect the galaxy as a whole? This is the AGN feedback problem, one of the most important unsolved problems in galaxy formation. The standard model of galaxy formation predicts that galaxies should be forming stars at rates much higher than observed. The molecular gas is there, the fuel for star formation, but in many galaxies, particularly large elliptical galaxies and the brightest cluster galaxies at the centers of galaxy clusters, the star formation rate is dramatically suppressed. Something is heating or removing the gas before it can collapse into stars. AGN feedback is the leading mechanism. The jets and winds from the central black hole, when it's active, inject energy into the surrounding gas, heating it, driving it out of the galaxy, preventing it from cooling and forming stars. The black hole regulates the galaxy's growth. Fermi has contributed to understanding this feedback in a specific way. By detecting gamma-ray emission from the lobes and hotspots of powerful radio galaxies, the systems where the AGN jet is currently active and inflating radio lobes visible at centimeter wavelengths, Fermi is probing the energy content of the lobes, the efficiency of the energy transfer from the jet to the surrounding gas, and the specific mechanisms by which the jet's energy is deposited in the intracluster medium. The specific finding is that the lobes of powerful radio galaxies contain more energy in relativistic electrons emitting gamma rays through inverse Compton scattering of CMB photons than the radio emission alone would suggest. The lobe energy budget is higher than radio observations implied. This means the jets are depositing more energy into the surrounding gas than previously estimated. The AGN feedback is more powerful. This has direct implications for galaxy evolution models. If the jets are more energetically powerful than radio-only estimates suggested, the feedback mechanism is more efficient, the black hole can suppress star formation more effectively, the galaxy's growth is regulated more tightly. The Fermi bubbles in the Milky Way are, in this context, a local example of the same feedback process that operates in thousands of galaxies throughout the observable universe. Our own galaxy was regulated, had its gas heated, had its star formation rate modified by the outburst from Scrane A times 2 to 4 million years ago. The exhaust of that regulation is still visible above and below the galactic plane. Let me now tell you about the most recent and most surprising Fermi result, one that's directly relevant to the dark matter problem, and that has generated enormous excitement and ongoing controversy. From the very beginning of the Fermi mission, scientists have been analyzing the gamma-ray emission from the galactic center, the region within a few degrees of Scrod times, for evidence of dark matter annihilation. The leading dark matter candidate for most of the past 30 years has been the WIMP, the weakly interacting massive particle. WIMPs, if they exist, can annihilate with their own antiparticles to produce gamma rays. The annihilation rate is proportional to the square of the dark matter density, its highest, where the dark matter is most concentrated, which is at the center of the galaxy. If WIMPs exist, The galactic center should be the brightest source of dark matter annihilation gamma rays on the sky. And the Fermi-lat, with its sensitivity to exactly the energy range where WIMP annihilation would produce gamma rays, is the ideal instrument for detecting them. What the Fermi team found, and what has been the subject of intense analysis and debate since 2014, is a specific excess of gamma ray emission from the galactic center. After careful subtraction of all known astrophysical contributions, the diffuse emission from cosmic ray interactions, the point source contributions from known gamma ray pulsars, and supernova remnants, there's an excess of gamma rays centered on the galactic center with a spectrum and morphology that is consistent with the predictions for WIMP dark matter annihilation. The galactic center excess, as it's called, has specific properties. Its spectrum peaks at a few GeV consistent with WIMP masses of 30 to 50 GeV annihilating through specific channels. Its spatial distribution follows the galactic center dark matter density profile with a specific power loss slope consistent with the expected dark matter distribution. Its normalization, the overall brightness, is consistent with a WIMP annihilation cross-section near the canonical value expected for a thermal relic. The consistency with dark matter annihilation is remarkable. It fits the theoretical expectations almost too well. But here's the complication. The galactic center is one of the most complex regions in the gamma ray sky. It contains an enormous number of astrophysical sources, young pulsars formed in the intense star formation near the galactic center, supernova remnants, cosmic ray sources, the radio arc, the molecular zone. Many of these sources are individually below the detection threshold of the Fermi-lat. They're not bright enough to be identified as discrete point sources, but collectively, an unresolved population of these dim sources produces a diffuse seeming emission that could mimic the spatial and spectral properties expected from dark matter annihilation. This is the millisecond pulsar hypothesis. Millisecond pulsars, old neutron stars, spun up to hundreds of rotations per second by accretion from a companion star, are efficient gamma ray emitters. They produce gamma ray spectra peaking at a few GeV exactly where the galactic center excess is seen. There's an established population of millisecond pulsars in the galactic field, and their spectra match the excess well. The question is whether there's a large enough population of millisecond pulsars near the galactic center to produce the observed excess. The debate has been running for a decade. Several statistical analyses using sophisticated algorithms to look for the specific statistical signature of an unresolved point source population versus a smooth diffuse emission have given conflicting results. Some analyses favor point sources. Others favor a smoother morphology more consistent with dark matter. The 2023 and 2024 analyses using the full 15-year Fermi LAT dataset with improved event reconstruction and background modeling have sharpened the picture without fully resolving it. The most recent analyses suggest that the galactic center excess has a morphology that is partially consistent with an unresolved point source population and partially consistent with a smooth dark matter-like component. The two contributions might coexist, some fraction of the excess from millisecond pulsars and some from something else. Something is producing gamma rays at the galactic center beyond what known astrophysical sources can fully account for. Whether that something is dark matter annihilation, the first detection of the universe's dominant matter component through its self-annihilation signal, or a population of unresolved compact objects, is the most consequential unresolved question in the Fermi mission. Now let me tell you about something that connects the galactic center excess, the Fermi bubbles, and the Blazer observations through a common physical thread, the specific role of magnetic field topology in determining what escapes from the vicinity of black holes. In all three of these phenomena, the Blazer jets, the Fermi bubble outflow and potentially the galactic center emission, the magnetic field near the supermassive black hole, is doing work in the blazar jets. The magnetic field is the transport medium for the Blandford-Znaic energy extraction and the driver of the jet collimation. In the Fermi bubble outflow, the magnetic field in the halo is the medium through which the relativistic electrons propagate and produce gamma rays via inverse Compton scattering. In the galactic center region, the magnetic field modulates the propagation of cosmic rays and the density of the dark matter distribution. The unifying physics is magnetohydrodynamics in curved spacetime, the behavior of magnetized plasma in the extreme gravitational environment near a rotating black hole. And the specific question that connects all three phenomena is what determines the magnetic field configuration in the inner accretion flow, and how does that configuration determine what escapes? Recent theoretical work informed by the detailed Fermi observations has identified a specific factor that matters, whether the inner disk is in a state called the magnetically arrested disk or MAD state, or in a more weakly magnetized state called the standard and normal evolution, or sane state. In the MAD state, the magnetic flux threading the event horizon is at the maximum value. The accretion flow can sustain the magnetic pressure at the event horizon is comparable to the ram pressure of the infalling gas. The magnetic field is strong, ordered, and coherent on large scales. The Blandford-Znaic mechanism operates at near maximum efficiency. The jet is powerful. The gamma ray emission is bright. In the sane state, the magnetic field is weaker and more disordered. The Blandford-Znaic efficiency is lower. The jet is less powerful. Less escapes. The transition between MAD and sane states, driven by the specific balance between the magnetic flux supply from the outer disk and the magnetic flux destruction by the turbulent inner disk, is what determines whether a given AGN produces powerful jets or weak ones, whether it creates structures like the Fermi bubbles or remains quiescent. 2 to 4 million years ago, the accretion flow onto Schrödinger A times transitioned into the MAD state, or came close to it. The magnetic flux on the event horizon reached a level sufficient to drive powerful jets. Those jets inflated the Fermi bubbles. Then the accretion rate dropped, the magnetic flux dissipated, and Schrödinger times returned to its current quiescent sane state. The bubbles remain slowly expanding as the evidence of that transition. This picture, where the history of a black hole's jet activity is encoded in the structures visible in the surrounding halo, is one of the most powerful frameworks that Fermi has contributed to. Every galaxy with a central black hole has a history of activity encoded in the specific morphology and luminosity of whatever halo structures its past outbursts have inflated. Fermi is reading that history from the gamma ray emission of those structures and reconstructing the activity cycles of black holes across cosmic time. Let me now address something that I think is underappreciated in discussions of the Fermi mission, the specific contribution that Fermi has made to understanding the relationship between gamma ray bursts and black holes, and what the specific properties of the GRB emission tell us about the conditions near newly formed black holes. Gamma ray bursts, the brief, intense flashes of gamma radiation that the GBM detects at rates of roughly 1 per day, are the most energetic explosions in the universe. We've discussed them in the boat conversation, but I want to focus here on what the Fermi data specifically reveals about the central engine, the physical object at the heart of the explosion, and how that central engine is related to the black holes we've been discussing. The central engine of a gamma ray burst is a newly formed black hole. In the case of long GRBs, those lasting more than 2 seconds, the progenitor is the core collapse of a massive rotating star. As the core collapses, the outer stellar envelope falls inward. If the core's angular momentum is high enough, a rapidly spinning black hole forms surrounded by a thick accretion disk of infalling material. The disk is dense, hot, and rapidly accreting. The black hole spins at near maximum rate. It was just formed from collapse. This is the most extreme version of the accretion and jet system we've been discussing. Not a billion-year-old supermassive black hole that has been accreting steadily a brand new black hole, stellar mass, spinning at near maximum rate, accreting at near maximum rate, threaded by the strongest magnetic fields that exist in nature. The Blandford-Znaiec mechanism operates at full efficiency. The jet power is at its theoretical maximum. The result is the most energetic transient in the observable universe. The jet, moving at a Lorentz factor of hundreds, punches through the collapsing stellar envelope, emerges from the star, and produces the gamma-ray burst as the jet material decelerates and radiates. What Fermi's GBM and LAT have revealed about this process is specific and important. The LAT has detected GeV gamma-ray emission from dozens of gamma-ray bursts, emission that is delayed relative to the prompt KeV gamma rays, continuing for hundreds to thousands of seconds after the prompt emission ends. This delayed GeV emission traces the afterglow of the radiation from the jet as it decelerates against the surrounding interstellar medium. The specific delay, the fact that the GeV emission starts later than the KeV emission, is telling us something about the gamma ray production mechanism inside the jet. The most natural interpretation involves the acceleration of electrons and the development of the magnetic field in the forward shock, which takes time to build up to the level needed for efficient GeV emission. The delay is a clock measuring the time scale for the physics to develop. For the extraordinary event GRB 221009A, the brightest gamma-ray burst ever recorded, the Fermi LAT detected photons at energies above 10 GeV, continuing for more than 2,000 seconds after the initial detection. These high-energy photons are traveling through an intergalactic medium filled with infrared and optical photons, the extragalactic background light, and the pair production absorption of these high-energy photons on the background light constrains the distance to the burst and the properties of the background light itself. This is a specific use of the escaping gamma rays as a probe of the universe between the source and us, using the absorption to measure the integrated optical and infrared emission of all the galaxies along the line of sight back to the distance of the burst. The extragalactic background light measurement from GRB 221009A and other bright Fermi GRBs is one of the most direct probes of the total stellar emission history of the universe. Something escaped, and on its way to us, it told us about everything it passed through. Now let me tell you about something that connects the Fermi observations to one of the deepest problems in theoretical physics, the question of Lorentz invariance violation. Special relativity is built on the postulate that the speed of light is the same for all observers, regardless of the frequency or energy of the photon. This is Lorentz invariance, the symmetry of physics under boosts. It's been tested to extraordinary precision in terrestrial experiments and in astrophysical observations. But in certain approaches to quantum gravity, certain ways of trying to reconcile quantum mechanics and general relativity at the Planck scale, Lorentz invariance might be violated slightly at the highest energies in ways that produce a specific energy-dependent modification to the speed of light, where higher energy photons travel slightly faster or slower than lower energy photons. This would be a tiny effect. The modification is expected to be suppressed by the ratio of the photon energy to the Planck energy, which is roughly 1019 GeV for A10. GeV Fermi photon, the modification would be 1 part in 1018. utterly unmeasurable over laboratory distances, but over cosmological distances, over billions of light years, even a tiny fractional difference in speed accumulates. A modification of 1 part in 10, 18 inches the speed of a 1 GeV photon traveling over 10 billion light years, 10^26 meters, would produce a time delay of roughly 10^8 seconds, several years. This is measurable. If a gamma-ray burst at cosmological distance produces both low-energy and high-energy photons simultaneously, and the high-energy photons arrive years earlier or later than the low-energy ones, that's evidence for Lorentz invariance violation. Fermi has been testing this for 15 years. The GBM provides precise timing of the prompt emission at keV energies. The LAT provides precise timing of the GeV emission. For every bright gamma-ray burst at known distance, the team compares the arrival times of photons at different energies and looks for systematic energy-dependent delays. The result is the most stringent test of Lorentz invariance ever performed, tighter by orders of magnitude than any laboratory experiment. For GRB 090510, a short gamma-ray burst at redshift 0.9, the analysis found that the arrival time difference between a 3:1 GeV photon and the main burst emission was less than 0.9 seconds. Over a travel time of more than 7 billion years, this constrains the Lorentz invariance violation scale to greater than the Planck energy for the specific parameterization where higher energy photons are slower. The laws of physics at the specific extreme precision that Fermi enables are consistent. Special relativity holds. Lorentz invariance is not measurably violated at the Planck scale by the class of modifications that would produce energy-dependent light speed. This is not a null result in the dismissive sense. It's an extraordinarily powerful constraint on quantum gravity theories. Every theory of quantum gravity that predicts energy-dependent light speed propagation at a level above the Fermi constraint is ruled out. The theory space for quantum gravity has been significantly reduced by gamma-ray burst observations. Something escaped, and on its billion light-year journey to Earth, it tested the foundations of special relativity to a precision that nothing else can achieve. Let me close this second part with something that I think is the most important framing for everything the Fermi telescope has done and is doing. Fermi is not just an astronomy mission. It's a physics mission in the sense that it's testing the fundamental laws of physics in the most extreme environments accessible to observation, not the controlled tabletop experiments of a physics laboratory, the uncontrolled natural experiments of the universe at its most extreme, black holes at the edge of their Eddington limit, neutron stars spinning hundreds of times per second, stellar explosions releasing more energy in seconds than the sun emits in its entire lifetime. In these environments, the laws of physics are pushed to their limits. The magnetic fields are the strongest that exist in nature. The gravitational fields are the most extreme outside of black holes themselves. The plasma is the most relativistic, the densest, the most energetically driven. The physics that operates in these environments, the magnetohydrodynamics of relativistic jets, the pair plasma dynamics of gamma-ray burst outflows, the inverse Compton scattering of relativistic electrons on photon backgrounds, is the physics of matter and energy at its most extreme. And Fermi is watching it all continuously for 15 years, building the most comprehensive catalog of extreme physics events ever assembled, thousands of gamma-ray bursts, hundreds of blazars monitored over years, the galactic center mapped to unprecedented sensitivity, the Fermi bubbles characterized in detail, the extragalactic background light measured across cosmic time. Something is escaping from black holes, in jets, in winds, in the outflows that inflate the halos of galaxies, in the gamma-ray photons that carry the information about frame dragging and magnetic field geometry and Lorentz invariance and dark matter annihilation across billions of light years. In part 3, I want to bring all of this together into the complete picture of what the escaping gamma rays are telling us about the universe at its most fundamental level, into what the Fermi bubbles mean for the future of the Milky Way, whether scramblized times will erupt again, what it would look like if it did, and what the evidence in the bubble structure is telling us about when and how the next outburst might occur. And into what I think is the deepest implication of the entire Fermi story, what it means that the most extreme physics in the universe is accessible to us, that photons from the immediate vicinity of black holes 1 billion light years away are arriving at our telescopes, that the universe is broadcasting its most intimate physical processes in gamma rays that we're only now learning to read. Something is escaping, and in what's escaping, in the gamma ray photons, in the energetic particles, in the electromagnetic waves, the universe is telling us everything about how its most extreme environments work. We just need to keep listening. So we'd arrived at this place where the Fermi Gamma-ray Space Telescope has been doing something extraordinary for 15 years, not just mapping the gamma-ray sky, but testing the fundamental laws of physics in the most extreme natural environments accessible to observation. The blazer jets, powered by the Blamford-Znaic mechanism extracting rotational energy from spinning black holes. The galactic center excess, that might be the first detection of dark matter annihilation. The gamma-ray burst constraints on Lorentz invariance that are among the most precise tests of special relativity ever performed. And the Fermi bubbles, those two enormous structures, 50,000 light years across, centered on our galaxy's central black hole, the visible exhaust of an eruption that occurred 2 to 4 million years ago. Now I want to bring it all the way home to ask what the Fermi bubbles specifically tell us about the future of the Milky Way, whether Scray times will erupt again, what that would look like, what the physics of the bubble structure is telling us about the black hole's activity cycle, to address the galactic center excess and what it would mean for physics, for cosmology, for our understanding of what the universe is made of if it turns out to be dark matter. And to close with what I think is the deepest implication of everything the Fermi telescope has revealed about the relationship between black holes and the galaxies they inhabit, about the universe's most extreme physics, and what it means that we can observe it from a planet orbiting an ordinary star, 26,000 light years from the nearest supermassive black hole. Let me start with the future. Because the Fermi bubbles are not just a record of the past, they're a prediction about what's coming. Scrawn A times is quiescent today. Its current accretion rate is extraordinarily low. It's consuming roughly the mass of our moon every year, converting most of that into radiation at an efficiency far below the Eddington limit. The luminosity of Scrawn A times in its current state is roughly 1033 watts, 1,000 times less than the luminosity of the sun. For a black hole 4 million times more massive, it's essentially asleep. But it wasn't always asleep. The Fermi bubbles are the proof. 2 to 4 million years ago, Scray times was doing something dramatically different, accreting at a much higher rate, driving powerful jets that punched through the galactic disk and inflated the structures we now see glowing in gamma rays. What caused the outburst? This question has been debated since the discovery of the bubbles, and the answer has implications for whether and when another outburst might occur. The most likely trigger was an episode of enhanced accretion. At the galactic center, several mechanisms can deliver gas to the black hole at elevated rates. The most dramatic is a close encounter between CGR-A times and a massive molecular cloud, a dense concentration of gas that, if it falls within the tidal radius of the black hole, is disrupted and partially accreted. The galactic center contains several molecular clouds, and their orbital dynamics can bring them periodically into the vicinity of the black hole. Another mechanism involves the star formation that occurs in the central parsec, the innermost light years of the galaxy. Young, massive stars formed in the dense gas near the galactic center lose mass through stellar winds and eventually explode as supernovae. This stellar mass loss delivers gas to the accretion flow, potentially triggering periods of enhanced activity. The timing evidence from the Fermi bubbles, an outburst 2 to 4 million years ago, coincides suggestively with evidence for an enhanced star formation episode in the central parsec, roughly 3 to 6 million years ago. The stars formed then, the young massive stars whose remnants are still present in the galactic center region, shed enormous amounts of gas through their winds as they evolved off the main sequence. That gas may have fed SCRO-A, triggering the accretion episode that drove the jets that inflated the bubbles. If this interpretation is correct, if the Fermi bubble outburst was triggered by the accretion of gas from a past star formation episode, then future outbursts depend on future star formation near the galactic center. And there's evidence that a new episode of star formation near SCRO-A times is underway. The G2 cloud, a diffuse gas cloud whose close passage to SCRO-A times in 2014 was intensively monitored by telescopes worldwide, survived its closest approach largely intact, but its passage deposited material in the accretion flow. Additional dense gas structures are orbiting in the central parsec, and some of them will pass close enough to SCRO-A times over the next millions of years to potentially trigger elevated accretion. Will SCRO-A times erupt again? Almost certainly yes. The question is when. The timescale is geological millions of years, not human. But the evidence suggests that the activity cycle has a period of perhaps tens of millions of years, driven by the episodic delivery of gas from the surrounding molecular zone. An eruption is coming. Not soon, by human standards. But in the lifetime of the Milky Way, a galaxy that will survive for trillions of years, the current quiescence is a brief pause between outbursts. What would the next eruption look like? This is a question that the Fermi bubble morphology allows us to answer with specific physical detail. The bubble structures that Fermi detects are the result of an outburst that lasted roughly 1 to 2 million years, a sustained episode of jet activity during which the jet continuously inflated the lobes. The jet power required to produce the observed bubble size and energy content given the estimated age of the structures is roughly 1037 watts, or about 10 million times the luminosity of the Sunday. This is a powerful jet, by any standard comparable to the jets of the more powerful radio galaxies observed at cosmological distances, but not at the extreme end of what active galactic nuclei can produce. If SCRO-A times were to undergo a similar outburst today, if the accretion rate suddenly increased to the level required for jet powers of 1037 watts, the effects on the Milky Way would be observable but not catastrophic for life on Earth. The most direct effect would be a dramatic brightening of SCRO-A's A times in all wavelengths. In X-rays, it would become the brightest persistent source in the sky, outshining every other X-ray source by orders of magnitude. In gamma rays, it would produce a diffuse glow across the galactic center, visible with any future successor to the Fermi telescope. In radio waves, the jet pointed perpendicular to the galactic plane would produce bright radio lobes visible with any current radio telescope. The jet itself would not pose a direct threat to Earth. The jet axis would be perpendicular to the galactic plane, pointing toward the north and south galactic poles. Earth orbits in the plane of the galaxy, roughly 26,000 light years from the galactic center. We're not in the jet's path. The indirect effects would be more subtle but potentially significant over geological timescales. The cosmic ray flux at Earth would increase the enhanced activity near the galactic center, would accelerate more cosmic rays, and the higher cosmic ray flux in the galaxy would eventually reach Earth, potentially affecting the atmosphere and the surface radiation environment. The timescale for this effect, cosmic rays diffuse through the galaxy on timescales of millions of years, would be slow by human but not geological standards. The ionizing radiation from the enhanced accretion would increase the X-ray and extreme ultraviolet flux from the galactic center. At 26,000 light years, this increased flux would be absorbed by Earth's atmosphere and would not directly threaten life, but it would affect the chemistry of the upper atmosphere and potentially the ozone layer. On balance, the next eruption of Scrad-A, whenever it occurs, would be an extraordinary astronomical event, visible without telescopes as a bright star-like object at the galactic center, with extended structures visible even to the naked eye over months to years of activity. Scientifically transformative, providing a front-row view of jet formation and galaxy-scale feedback processes, potentially affecting Earth's biosphere over geological timescales through enhanced cosmic ray flux, but not catastrophic, not an extinction event. The Milky Way has survived previous eruptions, including the one that created the Fermi bubbles with its structure and its life-bearing planets intact. The next one will be extraordinary to witness, not lethal to witness. Now let me address the galactic center excess directly and say what I think needs to be said about it clearly and honestly. The galactic center excess is real. After 15 years of analysis with increasingly sophisticated methods, better background models, better point source catalogs, better statistical techniques, the excess persists. It is not a systematic artifact of the analysis. Something is producing gamma rays at the galactic center above and beyond what known astrophysical sources account for. The two leading explanations, dark matter annihilation and an unresolved population of millisecond pulsars, remain in contention. The most recent analyses using machine learning techniques to distinguish the statistical signatures of point source populations from smooth diffuse emission give results that are frustratingly not fully decisive. Some analyses favor point sources. Some favor a smooth component. The truth might be both. Let me be precise about what the dark matter interpretation would mean if it turns out to be correct. The WIMP dark matter that the galactic center excess is consistent with has a mass of roughly 30 to 50 GeV, about 30 to 50 times the mass of a proton. Its annihilation cross-section, the rate at which two WIMPs annihilate when they meet, is approximately 10 negative 26 cubic centimeters per second, which is exactly the canonical value expected for a thermal WIMP relic. A particle that was produced in thermal equilibrium in the early universe, decoupled from the hot plasma as the universe cooled, and is now present in the Milky Way's dark matter halo in exactly the observed abundance. This coincidence between the annihilation cross-section implied by the galactic center excess and the cross-section required to produce the correct relic abundance in the early universe is sometimes called the WIMP miracle. It's the reason WIMPs have been the leading dark matter candidate for decades. The same physics that explains the dark matter abundance today explains the signal in the galactic center if the signal is dark matter, if the galactic center excess is dark matter annihilation, if the machine learning analyses and the continued Fermi monitoring and the forthcoming next generation gamma-ray telescope observations eventually confirm the smooth spatial morphology and the spectral shape that dark matter predicts, it would be the most important discovery in physics in a generation. Not just because it would identify the nature of the dark matter, because it would establish the existence of a new particle, a WIMP, at a specific mass and coupling, providing the first direct evidence for physics beyond the standard model from an astrophysical observation. It would connect the largest scales in the universe, the distribution of dark matter in galactic halos, to the smallest, the specific interactions of a new fundamental particle. It would confirm a theoretical framework, the WIMP thermal relic scenario that has been developed over 40 years, and it would mean that the central black hole of our own galaxy is surrounded by a dense concentration of annihilating dark matter that CGRA times sits at the center of a dark matter spike, a gravitationally concentrated peak of the dark matter density profile, producing a sustained gamma-ray glow that Fermi has been detecting for 15 years. Something is escaping from the galactic center. If it's dark matter annihilation, if the WIMPs are annihilating in the dense gravitational field near scRAN A times, and the products are escaping as gamma rays, then we are detecting the universe's dominant matter component annihilating itself in the vicinity of our galaxy's central black hole. The implications are extraordinary, and the answer, definitive, unambiguous, settled, is not yet in. But the data is accumulating, the analyses are improving, the next generation of gamma-ray instruments, the Cherenkov telescope array, currently under construction in Chile and the Canary Islands, will provide an order of magnitude improvement in sensitivity above 100 GeV, allowing a much more precise characterization of the galactic center emission at high energies where the dark matter and millisecond pulsar models make different spectral predictions. The answer is coming. Let me now connect everything, the Blazer observations, the Fermi bubbles, the galactic center excess, the gamma-ray burst constraints, into the single most important conceptual insight that the Fermi mission has produced. It's the insight about the relationship between black holes and the structures they inhabit. Not just the galaxies, though. The galaxy-scale feedback of AGN jets on star formation is a crucial part of the story. The larger structures, the cosmic web, the universe itself. We've established throughout this series that the universe has a specific large-scale structure. Filaments and voids, galaxy clusters and cosmic walls, the hierarchical assembly of structure from small scales to large. This structure is built from dark matter, the gravitational scaffolding, with ordinary matter following the dark matter halos and forming galaxies at the nodes of the cosmic web. But the specific properties of the galaxies that form in this structure, their sizes, their stellar masses, their star formation rates, their morphologies, are not determined by the dark matter alone. They're regulated by the feedback from the central supermassive black holes. Without AGN feedback, the models predict galaxies that are too massive, too blue, too star-forming, too bright. The gas cooling is too efficient. It would collapse into stars at rates far higher than observed, producing galaxies far more massive than the most massive galaxies we see. Something prevents the cooling. Something heats the gas. Something limits the star formation. That something is the jet. The same jets that Fermi detects as gamma-ray emission from blazars, the same jets that inflated the Fermi bubbles in our own galaxy, the same jets that are currently inflating the radio lobes of powerful radio galaxies and galaxy clusters throughout the observable universe. The jet is the universe's thermostat. When the central black hole is accreting rapidly, when gas is flowing in from the surrounding galaxy at a high rate, the jet turns on. It injects energy into the surrounding gas, heating it, driving it outward, reducing the cooling rate, slowing the star formation. As the star formation slows, the gas supply to the black hole decreases. The accretion rate drops. The jet weakens or turns off. The gas cools again. Star formation resumes. The gas supply to the black hole increases. The jet turns back on. This feedback cycle, operating over millions to tens of millions of years, regulates the coevolution of the black hole and its host galaxy. The black hole grows when gas is available. Its growth is limited by the jet it produces when it's large enough. The galaxy's star formation history is shaped by the activity cycles of its central black hole, and the galaxies we observe today, their specific distribution of masses and star formation rates, the specific luminosity function of the galaxy population, the specific properties of the most massive ellipticals at the centers of galaxy clusters, all bear the imprint of this regulation. All carry the fingerprint of billions of years of AGN feedback. Fermi is reading these fingerprints. in the gamma-ray emission of blazar jets, in the structure of the Fermi bubbles, in the lobe emission of radio galaxies. It's reconstructing the activity history of supermassive black holes and their jets, not just in the Milky Way, but across cosmic time, and building the picture of how black holes shape the galaxies and ultimately the universe that we inhabit. I want to say something now about what the Fermi mission represents, not just as a scientific instrument, but as a moment in the history of human observation of the cosmos. Before Fermi, the gamma-ray sky was known only in outline. The EGRET instrument on the Compton Gamma-ray Observatory, Fermi's predecessor, had mapped the sky at GeV energies in the 1990s, finding hundreds of sources. But its sensitivity, resolution, and monitoring cadence were limited. The detailed, time-resolved, spectrally precise picture of the gamma-ray universe was not accessible. Fermi changed this. In 15 years of continuous monitoring, it has detected more than 6,000 individual gamma-ray sources, blazars, pulsars, supernova remnants, star-forming galaxies, gamma-ray bursts, the sun during solar flares, the Earth's limb during lightning storms. It has provided tens of thousands of individual gamma-ray burst detections. It has built the most complete picture of the high-energy universe ever assembled. And in doing so, it has revealed something that I think is genuinely humbling. The universe at its most extreme, the black holes and their jets, the spinning neutron stars, the exploding massive stars, the annihilating dark matter, is not hidden from us. It's broadcasting. In gamma rays that travel unimpeded across billions of light years, carrying information about the physical conditions at their source with extraordinary fidelity, we are not isolated. We are not cut off from the universe's most extreme physics by distance or by opacity. The gamma rays from blazars a billion light years away are arriving at Earth right now, reaching our detectors, encoding information about magnetic field geometries, near event horizons, and the rotational energy of spinning black holes, and the specific physics of relativistic jets. The products of dark matter annihilation, if that's what the galactic center excess is, are reaching us from the center of our own galaxy 26,000 light years away. The universe is talking to us. In the most energetic language available, gamma rays carrying billions of times the energy of visible light. And the Fermi telescope has been listening continuously for 15 years. Something is escaping. Let me return to that sentence, the sentence I started with, and complete it with everything we've established. Something is escaping from the immediate vicinity of supermassive black holes. Gamma rays produced in magnetic field structures within fractions of the Schwarzschild radius of the event horizon are escaping the radiation fields that physics says should absorb them, powered by the relativistic motion of the jet that reduces the apparent photon density in the jet rest frame, and ultimately by the rotational energy of the black hole itself, extracted by the Blamford's-Nyack mechanism through the magnetic flux threading the ergosphere. Something escaped from the central black hole of the Milky Way 2 to 4 million years ago. An outburst of jet activity lasting 1 million years, releasing the energy equivalent of 100,000 supernovae, inflated 2 enormous lobes of relativistic plasma that we now see as the Fermi bubbles, glowing in gamma rays across 50,000 light years of the galactic halo. Something is escaping from the galactic center right now. A diffuse glow of gamma rays, the galactic center excess, whose spectrum and morphology are consistent with the annihilation of dark matter particles in the dense gravitational environment near Scray. If confirmed, it would be the universe's dominant matter component betraying its presence through the gamma rays produced when 2 WIMPs meet and annihilate. And something escaped from the depths of massive stars at cosmological distances. The gamma-ray bursts that the Fermi GBM detects daily, whose high-energy photons travel billions of light years and arrive with the timing precision needed to test whether the speed of light depends on photon energy, placing the most precise constraints on Lorentz invariance ever achieved. All of this, everything I've described in these three parts, is the story of what escapes, not from the interior of black holes. Nothing escapes from inside the event horizon, and Hawking radiation aside, quantum effects don't change this in any observable way. But from the environment of black holes, from the accretion flows and the jets and the magnetospheres and the dark matter halos, and the energetic outflows that black holes drive, the escaping gamma rays are carrying information about the magnetic field topology near rotating black holes, about the accretion history of our galaxy's central black hole, about the nature of dark matter, about the validity of special relativity at the highest photon energies, about the coevolution of black holes and galaxies across cosmic time. This information has been traveling toward us across millions or billions of light years. It arrived at the Fermi Gamma-ray Space Telescope, which has been faithfully recording it photon by photon for 15 years. And the scientists analyzing that data have been translating it, decoding the information carried by the escaping gamma rays into the specific, extraordinary, physically precise discoveries we've been discussing. I want to close with something that I think is the most important thing that can be said about the Fermi mission and about what it represents for physics. The universe doesn't care whether we understand it. The gamma rays from blazars have been escaping for billions of years, long before there were any detectors to catch them, long before there were any minds to interpret them. The Fermi bubbles have been expanding for 2 to 4 million years, long before our species existed to look at them. The dark matter has been annihilating in the galactic center for the entire history of the Milky Way, producing gamma rays that have been crossing the galaxy undetected until 2008. The physics was happening, the gamma rays were escaping, the universe was doing what it does, running its processes, following its laws, producing its extraordinary structures and events without any witness. And then we built Fermi, not because we knew what we would find. We suspected blazars would be bright, they were. We hoped to detect pulsars, we found hundreds. We knew gamma ray bursts were there, we detected thousands. But the Fermi bubbles were completely unexpected. The galactic center excess was not predicted. The quasi-periodic oscillations encoding frame dragging in blazar variability were not anticipated. The Lorentz invariance constraints from gamma ray bursts exceeded all theoretical expectations for what would be achievable. The universe had been producing these phenomena. We had not been listening. Then we built an instrument, launched it into orbit, and began to listen. And the universe, indifferent, unknowing, following its laws, delivered the information that 15 years of collected gamma rays encodes. This is what observation does. Not reveal a universe that was waiting to be revealed. Encounter a universe that was happening regardless, and extract from that happening the specific information that human minds can use to understand it. The Fermi bubbles are not more real because we discovered them. They were there before, they'll be there after. Our discovery changed nothing about them and everything about our understanding of the galaxy we live in. Something is escaping. It was always escaping from the jets of blazars, from the center of the Milky Way, from the depths of massive stars, from the annihilation of dark matter particles in the galactic gravitational well. We built an instrument sensitive enough to catch it. And in catching it, in 15 years of continuous gamma ray monitoring, in thousands of detected sources, and tens of thousands of detected bursts, and millions of detected photons, we have assembled the most detailed picture ever produced of the universe at its most extreme. The picture is not complete. The galactic center excess is not yet resolved. The specific magnetic field configuration that produces the most compact blazar emission zones is not yet fully understood. The specific trigger for the CGR A times outburst that created the Fermi bubbles is not confirmed. The relationship between the dark matter density profile and the observed excess morphology still has uncertainties. but the picture is extraordinary, more detailed, more precise, more physically rich than anyone who designed the Fermi mission could have fully anticipated. Something is escaping. And in what's escaping in the gamma rays from the most extreme environments in the observable universe, the universe is telling us, in the most energetic language available, the story of its own most extreme physics. We are listening more carefully, with more sensitivity, over a longer baseline of continuous monitoring than at any previous point in human history. And the universe, indifferent but informationally generous, is answering